So I'm going to talk about some work that we've done over the last 2 years or so on an arithmetic scheme, which is designed for mainly deep learning training, but also it can be applied to inference. Before I start,
This is Sydney.
Yeah, I'll just describe my lab, which is called the Computer Engineering Lab. And we focus on how to use parallelism to solve demanding problems. And we work on novel architectures, applications, and design techniques, mainly using FPGAs. And our research is on reconfigurable computing. And more recently, we've been working on radio frequency machine learning. So how you can apply machine learning to radio problems. And this is the group. So basically, in doing machine learning, there's usually a trade-off between precision and performance. And CPUs and GPUs are designed to support data types of fixed word lengths, such as doubles, floats, longs, shorts, etc. And as we all know, I guess, FPGAs and ASICs allow you to create custom data paths and support arbitrary word lengths, which is one key optimization that can be exploited to achieve acceleration over things like GPUs. So as you reduce the precision, then the peak performance that you can achieve per given area improves. And the number of weights that you can store on device improves. And so, you know, these are large factors, about 200 times when you go from 32 bits to 1 bit in terms of peak operations per second, and about 30 times when you go from 32 bits to 1 bit in terms of the amount of weights that the number of weights that you can store. So the problem that we're trying to address is how we can utilize low precision for which people have been doing for a long time, and also training. So I'm going to talk about 3 things. First, I'll describe block Minifloat, which is our arithmetic scheme that was developed. And then about how we applied it to time series prediction, which is inference first and then training of a time series prediction neural network design, and then transfer learning for convolutional neural networks. So the work on block Minifloat was done by Sean Fox, who graduated about 1.5 years ago and is now at Qualcomm. And so in doing on FPGA training, there's it's much harder than inference, because inference, basically you take input, which could be a large number of images or something like that, and it kind of, you have this big image, and then at the end you have one number, which is the class or something like that. In training, what you have to do is that you have to do the forward propagation, which is inference, and then you have to back propagate. When you do that, you need to have all the activations, and you have to back propagate with respect to the weights and also the activations. So that's roughly 3 times more multiply accumulates per second, and it has much higher memory requirements. And people have proposed specialized arithmetic schemes as alternatives to FP32 and FP16. Actually, in IEEE language, these should be called binary 32 and binary 16. That's the official term for it. And in fact, there's a working group which is trying to define an 8-bit format for FPGA training, which they're working on right now. And it turns out that it is possible to do training with 8-bit weights, activations, and gradients, 4 to 8 bits. And of course, if you can do that, then it's cheaper and faster. It can lead to cheaper and faster training systems. We were discussing at the FPGA conference last week that to train GPT-3 costs roughly $5 million per run, because the way that this was Mike Hutton from Google that said this. So it's roughly, so how much does a GPU cost per day? Let's say $10. And GPT-3 takes 10,000 GPUs 3 months to train. So that's just the final run. But as we all know, to train a neural network model, we probably need to do that 100 times before we get to the final model. So that would be $500 million. So even Google worried about this, you know, as being computationally expensive. So if we could reduce that by a factor of 2 to 4, then that would it will still be outrageously expensive, but not as bad.
Why not sure about data center?
So our work is mainly focused on the edge. I'm not sure whether there is a good story for FPGAs in the data center. You know, this could be argued. So let me first describe what block Minifloat is. So Minifloat is easy to explain. It's just a narrow floating point representation. So the range that we studied is between 4 to 8 bits. And we don't support not a number in infinity. Apparently, I was talking to somebody who's on the working group for this new floating point format, and there are arguments about all of these issues between the different companies. But basically, it's a conventional format which is similar to IEEE 754, which I guess many are familiar with. There's a sign bit, a number of exponent bits, and a number of mantissa bits, and a Minifloat is same format, except with smaller number of exponent and mantissa bits. So the advantages of this are that it crafts fewer bits, so it takes up less memory, and the hardware implementation is smaller. The disadvantage is because you have fewer exponent bits, then the dynamic range, the range of numbers that you can express is smaller. Now, block Minifloat, as the name suggests, is a number of Minifloat numbers. So imagine a Minifloat tensor here. And so this has 1 sign bit, 4 exponent bits, and 3 mantissa bits in this example. And you have a number of these. Actually, in the experiments that I'll describe, it's a 48 by 48 2-dimensional block. And there's a shared exponent bias. So here are the, you have a tensor, which is these Minifloats, and amongst a large number of these, you have a shared bias. Okay, so that means that you can shift the range of these Minifloats to, to the right place. And the range is dynamic. So we can describe a very wide dynamic range with a small number of bits. And the advantage of using these Minifloats is that you can describe very dense dot products in hardware. You can implement dense dot products in hardware. This doesn't come out very well. Now, the main problem that arises when the main design decision that arises when you use block Minifloats is, suppose you have this this Minifloat, it can only represent a relatively small range of numbers, which is in yellow. Just barely make it up. Yeah. And the problem is that the numbers, the tensor that you want to represent could be even wider than the numbers that than the Minifloat format. So that leads to the problem. Well, how do I align this block Minifloat? I've only got, I'll go over here, tripping over my cables. So I've only got this much range of the Minifloats, and I want to, put it somewhere in here. Where do I put it? What one strategy could be, okay, well, I'll align it with the mean or the median or, something. We chose to align it with the maximum value. So that means, and the reason that we do it this way is when you're doing a dot product, what's important are the large values. If the small values underflow, then we just let them underflow. But we make sure that, we stay in this range of the large values. And we'll show us some experiments later that turns out to be a good choice. So just to summarize, you can have fixed point tensors, which many people have implemented inference with. You can have tensors which are Minifloat numbers, which there's been research using that, small floating point formats. Block floating point is a format which has been used for many years, which uses a shared exponent and fixed point numbers. And what we're proposing is block Minifloat, which has a shared exponent amongst these small floating point numbers. And what I was trying to say a bit earlier is that block Minifloat is actually a superset of all the other formats, in that, the other three formats are a special case of block Minifloat. And if you had a library which implements block Minifloat, then you can have all the other formats as special cases. So if you choose a format with, say, only exponent bits, then that's actually a logarithmic number system. If you choose it with only mantissa bits, then that's a fixed point number system, and so on. There's one other important design decision that we made in implementing these block Minifloats, and that's to use what's called a Coolidge accumulator. One is a fixed point accumulator, which has sufficient bits so that it will give you the exact right answer for any input that you use. So fixed point accumulator, wide enough to compute error-free sum of the floating point products. So this gives us a number of very nice properties to our number system. For example, one is that we will get the same answer for a block that you will get on using IEEE 754. And I'll talk about that a little bit more later. And when we have small number of exponents, that means that we don't need to have a big shifter. And that leads to an efficient FPGA implementation. So we use three techniques to reduce data loss. The floating point number system that we use supports gradual underflow. We use we use blocks, so Minifloats, so block Minifloats rather than Minifloats. And we actually use hybrid formats. So we use a different format for the feed forward path as the back propagation paths. And because of the way the use of the Coolidge accumulator, we can simulate this block Minifloat hardware on a GPU using FP32 numbers, and we can be sure that it gives us the same result as our block Minifloat numbers. And we actually apply block Minifloat to all weights, activations, and gradients, which not all low precision training schemes do. Some low precision training schemes kind of have a mixed precision format where they keep some things in high precision and try to do the majority of computations in low precision. But we can keep most things in low precision in the scheme. And so, you know, we tried a whole bunch of different 8-bit, 7-bit down to 4-bit formats. And we actually optimized the format for different, this is the feed forward path, so 2 exponent bits and 5 mantissa bits. This is the backprop path, 4 and 3. So it turns out that you need more range in the backprop path. Now, here are some experiments that we ran to validate the design choices. So this first one shows the effect of denormal numbers. If you don't have denormal numbers, this is epochs versus the loss value. And if you don't use denormal numbers, then it just doesn't converge you. The green one is 32-bit floating point, and the blue trace here is 6-bit block Minifloat. And as you can see, it converges to the same loss value. Here, this shows the trade-offs that we get in selecting the block size. So if block Minifloats are only efficient if you can have relatively large block sizes. If you have small block sizes, then it kind of becomes a number system similar to floating point. And so the red line here is the area versus the block size. And the blue dots here show you the range that can be the tensors actually take. This is the dynamic range while you're doing training. And we wanted to work in this area where the area starts to flatten off. So we get the best area efficiency. And so this is 2 to the 5, this is 32 and 64. We actually operate in here at 48. So that means 48 by 48 blocks. And then in terms of the how we scale the Minifloats, remember right at the start, I said we scale so that we never overflow. So we scale to the maximum. And that puts us in this flat range here. So this is the root mean squared error of the dot product versus the exponent base. But basically we operate in this flat part where we have the least root mean squared error for our dot products. Now, so we haven't spoken about FPGA implementations yet. This is all on GPU. And so the way we do our forward activation is that we convert our numbers to block Minifloat values from a high precision. And we do that with stochastic rounding. So the weight, activation, and gradient tensors are quantized with stochastic rounding. Then we apply this dot product with the Coolidge accumulator, which ensures that they're exact. And also we can use the GPU's CUDA library directly if we make this decision. And then all the other things are done in 32-bit floating point in this example. And the basically we do similar things for the back propagation with respect to the gradient and the weights, as well as the weight update. And so we do approximately 1 floating point operation every, actually this should be n times n multiply accumulates. And there's a 5 times slowdown in doing training with block Minifloat compared with FP32, which is actually a lot better. So we can, for example, train ImageNet, whereas if you try to implement a low precision format without some of these features, then it could be like 20 times slower than 32-bit floating point. And in that case, it kind of starts becoming intractable to train even a relatively small benchmark like ImageNet. So here are a bunch of training experiments that we did. This is the validation error versus the number of epochs for ResNet 18 using ImageNet. And the 32-bit floating point result is this red one down the bottom here. And as you can see, as we increase the precision from 4-bit format down to this one is I think that one's this one, logarithmic 5-bit format, block Minifloat 5-bit format. This is 6-bit block Minifloat, 7-bit block Minifloat, and 8-bit block Minifloat. You can see that they all converge, and by the time you get to about 6 bits, it's very close to 32-bit floating point. This is a small transformer. This is German to English machine translation, and the metric is this blue score. And this is the number of epochs. And we observed that our 8-bit block Minifloat format got very close to 32-bit results. We ended up running a bunch of them: AlexNet with the ImageNet set, EfficientNet, an LSTM, a transformer, and an object detector. In all cases, our 8-bit block Minifloat format was very close to 32-bit floating point. In order to understand the area efficiency, we synthesized a fuse multiply add and a 4x4 systolic array multiplier using block Minifloat with the Cadence RTL compiler and at 28 nanometers. And what we saw is that the block Minifloat 8 area and power is comparable to IM8 with a 32-bit accumulator. So this is the systolic array, which is probably the best comparison. Block Minifloat is about 700 square microns, sorry, 7,000 square microns for IM8 and block Minifloat 8, and about the same power. And this is, you know, at least a bit less than half the area of an 8-bit floating point format. So we actually compared the block Minifloat designs with some other low precision block formats, low precision formats designed for training from IBM and other places. And this is the top one accuracy for ImageNet ResNet 18. And this is the computational density, which is but basically the area that you require to implement it. And in all cases, we actually got better density than the other ones for the same accuracy. So that was the kind of number system. Now let's look at FPGA implementations. So Wenjie Zhao is actually working on time series prediction. And there's a time series predictor which is called NBeats. It was developed by Benjo's lab in Montreal, and we looked at inference and training using 4 to 8-bit precision block mini floats. So the NBeats model, NBeats stands for Neural Basis Expansion Analysis for Interpretable Time Series Forecasting, and it's a model proposed in 2019 and achieved state-of-the-art time series prediction results, so time series regression. And the neural network consists mainly of fully connected layers with shortcut connections. So these are kind of fully connected layers, and they're kind of these shortcut connections which bypass the block, so residual block. We developed a inference accelerator, which basically has a matrix multiplier, a small number of buffers, and then a vector addition and another thing to do exponent alignment and the ReLU. And each processing element basically does a multiplication and a Coolidge accumulation. And it also supports the translation from this Coolidge fixed point format back to block Minifloat. In terms of accuracy, we tested it on, there's a benchmark set called the M4 competition, and the FP32 and BM8 are in the red and orange colors, and as you can see, we get same accuracy as 32-bit floating point. Int 8, so for this score, the smaller value is better. In 8, we get this green one. And so the accuracy of 8-bit block Minifloat is similar to 32-bit floating point. In terms of resource utilization, so int 8 and BM8 are the orange and blue ones. So this is block Minifloat 8 in blue. It uses less DSPs than int 8 or FP16. It uses roughly a little bit more in terms of ultra RAMs in our design. In terms of block RAMs, it uses less resources, and so it's actually very efficient on an FPGA.
So this is the particular, is it ResNet 32 or which?
So this is NBeats. This is the time series predictor. So mainly fully connected layers.
Okay.
Yeah. So from this analysis, we concluded that the area of block Minifloat 8 is similar to int 8, but smaller than FP16, which is the one in gray. This is the inference performance. The power of all of them is roughly the same. The peak performance for block Minifloat 8 is on the bottom here. It's roughly the same as int 8. Latency is the same as the int 8 one, and the frequency we've achieved is the same as int 8.
Is that the FPGA or the ASIC?
This is FPGA implementation now. Yeah, this is on AlphaO. Can't remember which one actually, but it's one with HB.
Oh, okay.
No, and this is work which we haven't finished yet. We're working on a training accelerator, and so it's basically got a gem unit and a vector add, so that's similar to inference, and we have additional blocks to do stochastic gradient descent and other things. we're actually looking at a 2D systolic array architecture for that. And, you know, basically each processing element's a MAC unit. These are preliminary results for NBEAT's accuracy for training now. So before was inference, this is training. So an 8-bit block Minifloat format, we get the same loss as FP32. And with a 4-bit block Minifloat format, we can get only there's a slight degradation in the SMAPE loss. So the final part of this talk, I want to talk about this work that another student is working on at Leong in transfer learning. And you know, we're still kind of struggling to understand what is a really good application of transfer learning. But some reasons why one might want to do this on the edge is that for privacy and security reasons. So if you only process images at the edge, then you don't have to store any potentially personal information or send that data to the cloud. You can adapt to non-stationary data, as we discussed a bit earlier, and the size, weight, and power could be an improvement over something which has to send a lot of high-speed data to another machine far away. Also, if we do transfer learning, we might be, because we're starting from a pre-learned network, we could perhaps converge to a good solution faster. So in CNN training, if most of the layers are convolutional layers, then, well, in any type of CNN training, we have to do the forward propagation. If we're going to support ResNet, we have to support both unit stride and non-unit stride convolutions, which not all FPGA implementations do. So the forward convolution, I think everybody's familiar with. When we do the backward pass to generate the gradients with respect to the activations, then the operation is what's called a transpose convolution. And when we do the weight gradient, then that's called a dilated convolution in general. And we implemented data paths to do all of these in HOS. And so in the early work by Sean Fox, we had different precisions for our forward and backward propagations paths. However, when we're implementing an FPGA-based accelerator, we want to have one block that we can reuse both for the forward and the backward. So we chose a unified representation with 2 exponent bits and 5 mantissa bits. And we use a, I'll talk about this in a moment, but we use a fused batch norm and ReLU design. So we implemented all of these blocks, the unifying convolution block, which does the convolution and the transpose convolution. Then we have another block, which is called the dilated convolution block. So, you know, that's kind of what the data path looks like. We trained Cypher 10 from scratch using this design, and this was ResNet 20. We made one small change to ResNet 20, which is ResNet 20 kind of looks like this. There's a convolution, batch norm, ReLU, another 3x3 convolution, batch norm. And then we have this addition and then we have a ReLU here. What we changed it to is that we took this ReLU and moved it back into this block so that we can fuse these together. And what we checked was that for both the VGG-like network and the ResNet 20, we get the same, in doing this change, we actually get the same, we get the same accuracy. We don't lose anything by making this change. And we showed that we get the same accuracy for 32-bit floating point and this block Minifloat format. In fact, 2.5 and 4.3 gives roughly the same as this 2.5 format for this example. So the best accuracy that we achieved in all of these accelerators was with the 8-bit block Minifloat format. Then we applied it to a transfer learning application. When we first trained with the Cypher 100 benchmark set, and then we did transfer learning with the Cypher 10 benchmark set, and we changed the number of layers that we fine-tuned at the end. So we did not. So the weights, in this example, the weights here are all fixed, and we only fine-tune the final fully connected layers and a few convolutional layers. And here is the convergence. So this is iterations or epochs versus the loss. And with, if we do training from scratch in FP32, we get this blue line here. And if we do it with our transfer learning one, we get this, which actually converges to the same loss as the software. But because we're doing transfer learning, we do it much faster. Here's the resource and power. So if we do full updates, that means we update everything. Well, sorry, we made 3 implementations. One which was full update, we update all the weights. Second one where we update 6 convolution layers and the final fully connected layer. And then this one, 2 convolution layers in the final layer. So they all use roughly the same resources and power. And we go to this slide. If we look at the total latency, if we do full updates, we require about 3 milliseconds. If we only do 6 convolutional layers in the fully connected layer, this reduces to about 2. And then if we only do the 2 convolutional layers in the fully connected, it's about 1.5 milliseconds latency, which is half that of the full updates. We applied that to ResNet 20 and also a VGG-like network with similar results. So in conclusion, look, we believe that low precision formats have wide applicability for inference and training in edge applications. And even for training, if you use these low precision 4 to 8-bit formats, it doesn't necessitate a reduction in accuracy. We believe that you can do faster training using block Minifloats. So you can use fewer bits, store fewer bits. So that's important for memory bound problems. And narrow exponents and denser max means that for compute bound problems, it can be more efficient. And so I guess the thing that we think this is a really good solution for something, but we haven't been able to identify exactly what the really nice applications of this type of technology are. Thank you very much.
Questions? Any questions for Philip? Marco.
So when you use the normalized number, you are increasing the range. Have you tried to compare a mean block of 8 with no normalization and against the 6 with the normalization, both accuracy and resource utilization and so on? Because they should have more or less the same range.
So if you what you're asking is if you compare models with the same range.
Yeah, but you can achieve the same range with 6 and normalization, 6 bits for the exponent and normalization, and then the one with 8 bits for the exponent and no normalization. So these two cases should be more or less similar in the range that you can represent in the number. So did you try to see what the trade-off is by comparing these two?
Yeah. So actually, between the formats, like 0, 7 is kind of, we don't count the sign bit. So 0, 7 is like fixed point format. Then there's actually not a lot of difference between 2, 5, 0, 7, 3, 4. They all work, and one will work a little bit better than the other, and then we'll choose that one. But it's reasonably robust against what you choose there, and you think that's because of the block format. So there's been work by H.T. Kung and others in 4-bit block floating point training, and so with they've been able to do training with a simpler format than this one.
And just one last question. When you align the exponent, you may cause some catastrophic cancellation. Did you observe that, or is not relevant for training?
So yes, certainly it can occur, but it's not something that we've studied. And I don't think it's occurring because we get good accuracy.
Yeah,
but it certainly can, if you're unlucky, it certainly can. Yeah.
Thank you.
Maybe particularly in the small format. Oh no, that's right. No, we never get cancellation because of the Coolidge accumulator, right? Because the reason why you get cancellation is if you try to subtract two numbers that are very close together, right?
Yeah,
but we get the exact answer, so we never get cancellation in our thing. Yeah, our dot products will be the exact dot product result.
Oh, that's good.
Yeah.
Any questions?
Actually, I have a concern about the low bit training. When we have a new model, we train on the low bit training chip, like architecture. However, we have a very large accuracy loss. How can we know that the loss is because of the low bit, or is it because of architecture, or the new architecture, or anything else? Should we train this model on using the P32 to check that accuracy?
Well, that's what we've always done to date. And so we only have empirical results about, everywhere we've tried our thing, we've been able to drop in this 8-bit block Minifloat and get same as 32-bit floating point. But of course, there's no guarantee that, for a certain problem, it's not going to give a wildly different result. and I'm not sure what you can do about that apart from what you suggested, which is run it in 32-bit floating point, and which may not be too bad if you only have to do it once. But yeah, that's a good question, and I'm not sure how we can we can verify that the result that we got is a good one.
Is there a way to find the optimal representation for a given problem? We could define an optimization, objective function, and so on to figure out whether it's minimized area or highest performance or whatever for the correct or for the best Minifloat format.
No, I think because it's a nonlinear function, then everything that you'd want to know, like the accuracy and the power and all this, is nonlinear with respect to the model parameters. I don't think that you can do anything.
So the only way is to suck in and see.
Well, so actually we've been thinking about this. If the neural network were linear, so there's no non-linear parts, then you can apply conventional error analysis to it. And then you can actually bound the maximum error that you'll get and things like that, which may not be too helpful, right? You say, well, the maximum error is this big number, but it doesn't tell you much about your real problem. As soon as you introduce the nonlinear part, then for each possible activation, say you only have ReLU, right? Then it could be in one of two regions, right? If you have n different activations, then you have 2 to the n possible ways that that could go, and then the search space is not something that is really tractable, right?
Yeah. So does it mean that the result you're showing is specific to particular problems, and anything else may or may not be as optimized or may not be as accurate?
Yeah, but that's true for 32-bit floating point as well, right?
Yeah. Okay. And do you have a feel for how small one could sort of push that representation to be?
I think with a bit of work, you could get 4-bit results, which are similar to our 8-bit. But when you're talking about 4 bits, you really don't have much to work with, right? So, my feeling is that 8 is so you want a power of 2, right? So the only real choices are 2 or 8. Sorry, 4 or 8.
4 yes.
Right? Yeah. But 4-bit seems too close to the sun for me. So
2 would be
intuitively, it feels like 4 might be doable if you have studied the problem well beforehand. You have scaling factors and all this to make it work, but you wouldn't want to bet for a network that you've never seen before that you can do 4-bit training on it. But 8-bit seems to work quite well.
And when you're doing this, is it anyone try mixed precision or mixed mini block folding format in different regions?
So some of the works keep the weights entirely in 32 bits and then just calculate the gradients in low precision and then update the weights.
But is it uniform for the whole system? Or
no, so they have the high precision 32-bit stuff for the weight values themselves, and then they have kind of lower precision for the weight updates. In fact, most works are mixed precision.
With due respect to the mixed position. So I think the question for the look is that possible to have mixed position for different layers? Is that
But that's another possibility.
it's a mixed position for different layers? For example, first layer maybe it requires higher accuracy, so 32 bits or 16 bits. So I think that's a question. And my also my question.
So when you design the accelerator, you want to have you don't want to support different precisions, right? So if you have mixed precision, you'll have to have
But we can
different.
Yeah, but we can have the bit serial or let's say temporal basic units to support mixed precision. If you, for example, 4 bits, 8 bits, there's some they're not open source hardware designs which support base serial mixed precision communication. So actually you can run different positions using the same computer.
Mhm.
Yeah, I think that is very interesting. Yeah, just thinking about it.
I don't know, because when you talk about bit serial,
Yeah.
I haven't thought about it for super low precision, but I think that you know, if you take n cycles to do something,
Yeah.
then basically your bit serial has to operate at n times the clock frequency to get the same area time delay, right?
Or we can increase the power in another dimension. You know what I mean?
Yeah.
Yeah, for example, channel dimension or user dimension, spatial dimension. We can lower the power in the bit width, but increase the power in another dimension.
Yeah.
So we can still get the same thing, or maybe the power. That's just one thought.
Yeah, maybe, but you know, for neural networks, you can normally fill the chip with
Yeah.
whether it's bit serial or bit parallel, you can normally fill the chip with MAC units, right?
Yeah.
So you've got to have a better area time delay for it to be worthwhile. So if you're trying 16 bits, you've got to have 16-bit better. You know, it's hard, I think, to match a parallel one with a serial one.
Mhm.
For that, but for low number of bits, maybe you can.
Yeah, I've got another question. I don't have a very deep understanding of this low precision training, but I'm just wondering because according to everything here, I guess the low precision is probably done through training and then evaluating. But what if, say, you have a well-trained FP32 network, and then you directly convert all the parameters in FP32 to Minifloats? How would that affect the final, for example, accuracy of the network? Or
Yeah, that's something we haven't tried yet.
okay,
So normally, if you just convert all the parameters, then you might get a certain accuracy, and then which could be improved by doing further training. But no, we've mainly been looking at training from scratch and that kind of thing, which is, and we don't know those things in 32 bits in advance.